Okay, hi. I'm Andres. I work at Citus Data, and I mostly develop Postgres or try to play with Postgres. A lot of it around scalability, replication, and related tasks. And I'm going to talk about vertical scalability in Postgres, which means how can we work Postgres more efficiently on bigger machines. Now, that might be a bit strange because Citus Data more works on making Postgres work over multiple machines, but it's what I'm talking about. So, one question at first. Who of you knows about NUMA? Okay, that's actually more than I expected. And yeah. I'm going to come to the point why that's a problem and why it's actually a good idea as well. Who knows about cache coherency? And last question, who knows what an atomic operation is? Oh, wow, cool. So that makes it easier. So I'm going to talk about vertical scalability, which is the problem of making something work across multiple CPUs in a single machine or a single image system, whatever. And the goal is to have, by having more CPUs or more CPU cores in a system, to have higher throughput or something aligned with throughput. And the one big change in the last couple of years was that individual sockets in a system now have many more CPUs than they used to have. We used to have that a single socket around 2005 had 2 cores. We are now at 18. The CPU are now on the x86 market. The CPU is announced with 30-ish cores. In the non-x86 space, we have even more cores. So scaling across many cores becomes a more and more important problem. To a large degree, that's because of that it became very hard to make individual cores much faster because of physical limitations. So, and it also became more common to have servers with multiple sockets. That means several packages of CPUs in one server. We have now rather commonly 2-socket server. You can even rent them on AWS or any other cloud pretty much. In bigger installations locally, you often see 4-socket servers. I've seen Postgres run on 8-socket servers. Yeah, so those at 8 times 18 cores, you get a lot of cores. And another trend which changed a lot in the last 8-10 years is that we now have a so-called NUMA model, which I'm going to explain in 1 second. And the reason why vertical scalability is actually interesting and why we don't just try to scale across many machines is that it's actually often much easier to develop as a user for a larger machine instead of having to synchronize across many machines. One of the reasons for that is that while it's hard to scale something across multiple CPUs in one system, it's even harder to do that across several machines because the latencies are just 3-4 orders of magnitude higher between systems. You can have specialized technology that reduces that a bit, but it's still much more expensive. So it depends also very much on the type of task you're performing, what kind of choice of technology is more beneficial. So, and what is this NUMA and that you probably heard about before? In the old world, we had so-called uniform memory access. That means that all memory in the system was attached to one common bus, and all CPUs in the system, most commonly only one, was attached to that one bus. That means every time the CPU needed memory, it went to that common bus, and that went then to the memory, to the RAM, and that fetched the memory. That works kind of okay if you have 1, 2, 4 CPUs, cores, but once you have many more, if these individual CPUs here aren't just CPUs, but you have, say, a socket with 16 cores or 18 cores, then that bus becomes a bottleneck because everything goes over it. It also means that each individual CPU has to be able to address and control the entire memory in the system. And that is actually not that easy. So what we now have is that each socket in the system, again, a collection of CPU cores most of the time, has its own bus, and then each of these buses has their own access to the memory. And that means that you usually can have much more memory because each memory controller only needs to access the memory it has available locally. But it also means that if you want to access memory if CPU 1 wants memory that is not directly attached to it, it can't say, hey, bus, give me this memory. It has to go to CPU 2, say, can you give me that memory? And that obviously makes latencies higher. So it's a trade-off between faster access to local memory, but more expensive access to remote memory. And why am I bringing this up around scalability? One of the very common problems is that if you are not very careful and have around programming with shared data structures, you end up constantly moving memory between these systems. And if you are very, very unlucky, you don't move memory between the CPUs in their own caches, but you end up moving memory between the memory blocks, like the RAM on both sides. And that means you have latencies in the 180 to 250 nanoseconds, which in current CPU times is like a lot. Well, it's still 3 orders of magnitude faster than disk, but. So, what I'm going to talk about right now is how does Postgres implement concurrency in the most basic manner. And there's a locking hierarchy in Postgres where there's very, very low-level locks, and then there's built on those low-level locks, we have a higher, more complex set of locks. So the most low-level locking mechanism in Postgres are SpinLocks, and SpinLocks are really, really simple in the end. It's just saying one byte or bit saying, hey, this lock is free or not. And that means to get a lock, if it's not used, you just have to set that one bit. And if it's not free, you just wait until that bit gets unset. That works for many things. If you have only very, very short duration of the lock, if you have only do it to read 1 or 2 variables or set 1 or 2 variables, that works fine. But it has some drastic disadvantages. One of them is that it's exclusive only. There's no shared locks. If you have a spin lock, nobody else can enter the same protected section, which is bad if you just want to read the data, because 20 people can read the same memory location at the same time without any problems. And what also a problem is that they're called spin locks, and spinning there means that if the lock is not free, we are not going to say, hey, this process can't do anything. We are going to say, check this memory again, check it, check it, check it, check it, check it, and so on. So that means your CPU is going to be busy doing that and nothing else. And another, it's not really a problem, it's a property, is that in Postgres, SpinLocks have no error recovery path. That means if your process errors out while it holds a spin lock, you're screwed. And what the consequences of that is that it's not that you want to add error recovery, it's that you only use spin locks in the very, very short durations where you know there's nothing that can raise an error in between. And the other important thing is that there's only a fixed number of spin locks. You have to initialize a memory location, and that's a spin lock then. You can't have like a dynamic number of spin locks easily. And I'm going to explain why that's a problem. So on top of that, we have the so-called LW locks, and that stands for lightweight lock. They're still pretty damn fast, and they have the big advantage over spin locks that they are a reader-writer lock. That means you can have 20 processes can have the lock in a read mode and work concurrently, at least in theory. And the big another property now, which is contrasting them to spin locks, is that they have error recovery. If there's like an error while you hold a spin lock, while you hold an LW lock, that LW lock can get released. And that's very important if you consider something, hey, we are going to try to insert data into a page on the heap, and our write failed. We need to be able to recover from a failed write, or something like that. So these error recovery properties are very important, but that also means they're more expensive than SpinLocks. And they're also queued. That means, in contrast to SpinLocks, we don't hold the CPU in a busy state while we wait for the lock to be free. Instead, when we go to the operating system, say, hey, wake me up when the other guy is done. And it's also a fixed number. So, and the most common used lock that you actually see as a user is so-called heavyweight locks. And those are the ones that you see if you lock a table, if you type lock table, whatever. If you query PG locks, those are the ones that you see. And they have a much more complex semantics than either of the other technology locking primitives. And they also do error recovery. In contrast to all the others, they do deadlock checks, which means if you acquire them in any order that would otherwise just block indefinitely, we detect that and say, hey, one of you better abort, and we log an error message, which hopefully helps you to find what the actual issue is. And one more very, very important is that their number is basically dynamic. It's not like you can enumerate before when you start the database how many which tables exist in the system, which indexes exist in the system, and say, okay, this bit is only going to be used for this index or for this table. So there's like a hash table, and we use we can have a lot of different locks in there, and we don't need to know beforehand which those are. And again, they're built on top of LW locks and SpinLocks. Acquiring a heavyweight lock, which I'm going to talk about because we're talking about scalability, and those have been one of the biggest scalability improvements in Postgres, were around heavyweight locks. Works like we have this shared lock table where this dynamic number of lock entries. And to get a lock in there, we say, we lock the entire table. And then we search, hey, where's the right entry? And say, OK, this entry, which is identified in a hash table by the identity of the lock, is now locked. And then we can say, hey, now we can unlock the shared lock table. But you can kind of see that while we operate on that shared lock table, nothing else can operate on that table. Now, that was known as a problem long time ago. So there's not actually one lock table. There's by default, in earlier releases, there were 16. But still, the basic same problem exists. So what Robert Haas, a couple of years back, I think it was around 9.2, did was he thought, but most locks in Postgres on tables aren't actually conflicting. Because most of the time what you do is like, hey, you select from a table. And everyone can select from a table. And the locks that actually conflict with others are actually pretty damn infrequent, because how many times a day do you alter table? A couple hundred times maybe, but not billions. So what we want to have is a fast path for these locks. Instead, so whenever we acquire a lock, instead of directly going to the shared lock table, what you do is say, hey, is this lock one that conflicts with others commonly? And that's currently defined, would it block if it acquired itself again? And if there's no conflicting lock, what we do, we don't go to the shared lock table. We just say locally, hey, we now hold this lock. And then we're done. We can acquire it. That means we hadn't have to touch any of the shared state. And if you remember the NUMA diagram earlier, that means we didn't have to go to the memory or the caches of any other CPU. We could do it purely locally. But obviously, if you only record locks in your local structures, that's not going to help very much. So what we had to do is to make the other case, where we acquire locks that do conflict, more expensive. But since that's only happening seldomly, that's OK. So whenever we acquire a lock that's conflicting with others, we have to go to each other backend and say, does this other backend hold this lock currently? And then we go through each of them and say, OK, none of them conflict with the one I'm actually acquiring, because the lock held by backend 1 here, in this case, is, for example, an access share lock, which is not conflicting with anything but an access exclusive lock, and I'm only wanting to block writes. So I can acquire the lock. And that's then enough. There's a couple nitty-gritty details around this, like a couple hundred lines, but yeah. So, and the results are basically this, and I think this is super, super exciting. What I did here was not to take benchmark 9.2 against master. What I did was to say, I'm disabling this optimization in master, because otherwise the comparison would have been very skewed, because since then a lot of other optimizations have been added. So, but you can see that the orange line here is when we don't use this fast path mechanism, and you can see that at a few CPUs, like two threads, there's not much of a difference. At 4, you start to see a difference, but at high client counts, you see that it's like 5 times the throughput. And if you use a bigger machine than this hardware, then the benefits are even larger. So I think that's a pretty awesome improvement, and I think it shows the reason I'm bringing it up isn't generally, hey, I want to show this awesome diagram. Also, that's one reason. The primary reason is that it shows a very, very good technique to tackle concurrency problems, to tackle scalability problems. If you can have a fast path that avoids doing all the expensive work, and the cost of that is making the slow path that happens very, very infrequently slower, then that's usually a good deal. So that's one of the most common and most important tricks to avoid, to fix scalability problems. So that's my case one that I want to present. Who here has used perf in the past? Okay, that's a bunch of people. And who of you have profiled Postgres and saw a profile that looked like this? You're pretty much very happy about that, right? And you had a very hard time figuring out what's happening there. There's many cases. This is one of the most common cases where you see a profile like this, but the thing I'm talking about only fixes a number of these. But SLOC, to understand what this means, SLOC is the SpinLock implementation, and you will see that in the profile only when the SpinLock isn't actually free.
What is perf, by the way? What is perf?
Perf is a profiling mechanism. It can show which functions time is spent, most of the time is spent. So you can see that on this profile, I think it was on a 4-socket, 8-core each, 16 threads machine. 90% of the time was spent in SpinLocks. Obviously, that's not a good idea because you're not going to do anything. And the very, very important thing here is, in this workload, we actually had no writes. There was nothing that actually ever blocked, that it would, in theory, have to block because it was only reads. So unfortunately, we're going to have to look a bit at code. And this is how the the LW-lock implementation used to work. And you can see that to acquire lock, the first thing we do is to acquire a SpinLock, and then check, hey, is the lock we want to acquire a shared one? We check whether the current lock is currently held exclusively, because that's the only reason you can't acquire the shared lock. And if not, we can just say, hey, we also hold the lock. And if not, we put ourselves on a wait queue, release a SpinLock, and wait till the other guy wakes us up. But that's not all that interesting. And then after that, we try again. But who of you has already seen the fundamental problem if you want to acquire a shared lock with this algorithm? So the real problem here is that we acquire a shared lock and we hold a SpinLock. And if you remember it correctly, I said earlier that the SpinLocks is always exclusive. That means to acquire a shared lock, for a short time we hold an exclusive lock, which is kind of bad because that means the acquiring the lock is not actually shared. So that's something we had to fix because it really caused a lot of scalability problems. As you can see here, this is the profile, how it often looked. We scaled it very good until every CPU was, or every hardware core was actually busy, and after that it got really, really bad. And I've seen much more extreme examples of this, like where there barely was any throughput anymore, like we had basically no transactions happening at all anymore. And in this case, that's just a read-only PG bench, and that demonstrates the problem already. But if you have a workload that has like many nested loops, and stuff like that, then this might look much, much worse. So we gotta have to do something to fix this. So the trick here is to use atomic operations. Since not all of you knew what that is, that's basically operations on the CPU where you can manipulate memory directly in an atomic way. Because normally, if you want to do something like increment an integer, the way that works is to say, hey, I want this memory location back. Then you read it into the CPU. Then you say, hey, I want to increment this register in the CPU, and then I want to write it back. But if two people do that at the same time, you can lose one of the two writes. So what the alternative to that is that there's these atomic operations where you can say, hey, increment this memory address by 1 and do it in a way that's concurrency safe. You can kind of guess that these are rather expensive. Oh, but it's still better than holding an exclusive lock. So there's some complexities to do this around LW locks because, as I said earlier, they're queued, which means we want to enter the OS to wait till the other process that holds the lock is finished. So what we had to do is to check the lock twice. We first check whether we can acquire the lock. If we can acquire the lock, we're done. But if we not, what we have to do is to put ourselves on this wait queue and then try again. Because if we try it again, after that trying again, we can be sure that the other person that releases the lock has seen us. But if we didn't do this second check here, what could have happened is that in between the moment where we tried to acquire the lock and we queued ourselves, somebody else could have released the lock. And then we could have waited forever for the wake up because nobody else holds the lock, which is obviously not a very good idea. So instead, what we do is as soon as we queued ourselves, we try again whether whether we could now acquire the lock. And if so, we unqueue ourselves from the lock. And if it's still not free, we have to wait till the other guy releases us and we try again. And there's lots of complexity additionally around this, but this is the basic trick. And after that, the graph looks like this, which is what you want to see. And yeah, this is why the reason I picked this is twofold. One of them is I worked on it, and I'm kind of proud of it. So I'm not going to deny that. And the other thing is that it shows another approach to avoid these kind of problems. You can figure out basically two approaches, actually. It figures out, hey, do I actually need how heavy that lock is? Can I avoid taking it? And the second one is, can I use these atomic operations to do something that I previously couldn't? In this case, what this atomic try acquire does is basically this lock shared plus in an atomic fashion, plus some other complexities to handle actually exclusive locks. So, but yeah, we are much better up now with that. So, and the next issues I'm going to talk about, unfortunately, have required that you understand how Postgres handles disk data on storage. There's so-called shared buffers. Every time Postgres needs to read something from the disk, because you did a select star from table or something, it reads that data into shared buffers, and then processes the data there, and then returns it to you. And that's normally a good idea, because that means in many cases, all your data is in shared buffers, and you only ever have to access memory, and that's much faster than accessing disk, even if you have super fast PCIe SSDs. It's still like 2-3 orders of magnitude faster. So, and every page in this shared buffers cache has a descriptor that says, this page contains page 19 of relation A, or something like that. And that's just saying what's the content, and that's this tag. And then it has usage count. And the usage count is used for replacing the contents of this shared buffers, because obviously, in many cases, you will have databases that are larger than your memory. So you need to be able to replace parts of this cache with better, more interesting content. And the ref count is there so you don't replace content that actually is currently read. Because if you currently read something and then you evict it from the cache, that's going to be bad, because obviously your read is going to return something bogus. And again, there's a SpinLock. So in Postgres, buffer replacement basically works like using an algorithm that's called clock, which I'm not going to go into details here, but in the very simple description, it basically works that there is a clock which says we're at this position right now, and we look at this buffer. And until 9.5, that worked by first we take an exclusive lock around this that says I'm the only one that looks at this clock, and then said, hey, we look at buffer 0. Is this buffer currently used? If it has a ref count equals 0, we can't replace it because it's currently looked at. If it has a usage count above equals 0, OK, so nobody has used this, so we can use it. If it has a usage count above 0, we just decrement it and go to the next one. So what we do is we go to 0, and then to the next one, look at 1, and so on. And that means we sometimes have to go through all buffers to find any one that's actually not used. And actually, the usage count is capped at 5. So in many cases, we'll actually have to go 5 times around this. And if you have a couple gigabytes of shared buffers, that can take a while. And if you think, hey, but we hold an exclusive lock while doing this, yeah, then you're right. That's not a good idea. So if you have a workload that consists that's bigger than your shared buffers, then this can really, really hurt you badly. And there you get into the strange situation that if you have more shared buffers, the problem of finding cache replacement gets worse, which is, so it gets worse until you have it big enough. Then it gets much better. So it's not very nice. So we unfortunately haven't yet developed a better cache replacement mechanism. What we can do is to make the inefficient cache replacement mechanism more efficient, which doesn't improve the complexity or anything, but it makes it less bad. So again, the approach here is to say, hey, can we make this big, big lock more granular? And the approach there we took is to say, hey, we're not going to hold a lock during the whole sweep through all the buffers. What we do is every time we advance the clock once, we hold the spin lock. That was the first approach. And that made it much better. Then we said, but now we have this atomic operations that we can now use on every platform. Can we make this better? So yes, we could. It was actually rather easy because this clock cycle is basically just an integer that says, look at this buffer next. So we can just say, increment it by 1 every time. And the only problem then is that at some point you're going to run over the end here. At 21, you need to start again. But there's this nice CPU operation called the modulus. And so you just have to say, OK, we kept the number of we look at by n buffers and start again at the beginning. And there's a slight imbalance if you look at the last buffer, because some numbers are slightly more likely to occur, but that really only matters if you have a couple terabytes of data in shared buffers, which is not yet that common. So yeah, I don't have the super detailed profiles here because the tests take a long time to run. But because what we had to do, obviously, is to say, we need a shared buffer. We need data that's bigger than shared buffers. And often that means that how accurate the profiles are, it takes a long while for the profiles to get any sort of accurate and not very widely. And you can see that at a large number of clients, the efficiency difference between the two approaches, the one where we hold the lock all the time, and the one where we increment it 1 by 1 is quite large. But you also can see that it really only matters after you have a bunch of clients. And you see that we still have quite a bit of degradation if you have many clients. If you remember the graph for the LW lock improvement, it nicely tailed off at the end. It didn't get much faster anymore, but it didn't break down. And the reason there is that if you have many of these clock sweeps happening at the same time, all the backends have to look at shared state all the time. So what they're going to have to do is to ship memory from one CPU or from one memory controller to the other. And that means that bus in the middle actually becomes a bottleneck. That's why you see this slowdown. There's also a couple other issues, but this is a primary.
That shows EC2. Were these benchmarks done on Amazon? Or?
This one was on Amazon. The earlier ones were done on physical hardware, but at that time, I didn't have access anymore. Actually, yeah, because, it was on a dedicated instance to reduce the variability. And I would love to have rent somewhere to be able to say easily, hey, I want to have a large dedicated machine somewhere for 3 days, but apparently nobody does that yet. So, and also if EC2 started to have 4-socket machines, I would be very, very happy. But I don't think, I complained about it like the 3rd time now.
Working on it.
Good. Strange that I'm not the most important thing here. So, thanks. So yeah, on larger hardware, this actually looks much more extreme, but I didn't have the larger hardware to test this, so I had to make do what I had.
Is that 9.5 or head?
That's head as of, it's the same head. It's 9.5 as of 3 months ago, 2 months ago.
So that is in 9.5?
Yes, this is in 9.5. That's early 9.5, actually. Went in December. So I thought you meant which branch I was testing. So what we now have looked at is some common approaches. Hey, we can try to avoid the lock at all. We don't do any locking for the common case. That's a pretty cool approach. It's not always possible. Then we can make the locking more efficient. And that's what we did with LW locks. We can use atomic operations to achieve that, or we can replace the lock by doing atomic operations. That's another approach. And we can make locking more granular. These are quite common approaches to scalability problems. So unfortunately, we only fixed a bunch of these issues, not all of them. One of the ones that I think are the worst right now are the extension lock. Every time a relation is extended, that means like the physical file we've allocated isn't large enough. What we have to do is to take a lock. Nobody else can extend the relation at the same time, but reads and other updates can go on if there's enough space. And we do the extension and then release that lock, which means it doesn't really matter that much if you have like an old update-heavy OLTP workload where your files don't increase in size much. But if you do like parallel copies into the same file relation, this can bite you really bad. Then, as I said earlier, we have this buffer replacement problem. The current buffer replacement strategy is really inefficient. It has some nice properties, but it's really, really inefficient for large amounts of memory. And when the people came up with these algorithms, there was just not very much memory, so that didn't bother them much. Also, the other big problem is that our cache replacement strategy is very inaccurate. We have to come up with, like, which page do we evict? We have to come up with better choices to do that, because right now, we often evict the one that is like, hey, we need this page in 3 nanoseconds again. And we do it anyway. So that's something else we have to work on. And both of these are really only problematic if you have a workload that's larger than your shared buffer setting. If it's smaller, then we don't ever replace pages, so that's fine. And another very, very big problem is that currently there's so-called snapshots in Postgres, which are used to say, is this row visible to my transaction or is it not? And that's currently, from the complexity point of view, basically O for the number of connections, or the number of open transactions. And that's really bad. If you have like 300, 500 connections going on at the same time, that means a snapshot is getting rather expensive. And again, during the while we hold the snapshot, we hold an exclusive lock, hold a shared lock, which then is problematic if somebody else wants to commit. Now, this has gotten a bit better in will be a bit better in 9.6. Amit Kapila and Robert Haas have a nice like band-aid, I would say, maybe they would characterize it differently, but it really helps if you have both reads and writes going on at the same time. But still, it's not a fundamental fix here. There's another approach that has been talked about a lot, which is so-called CSN-based snapshot, but unfortunately, it's a very complex project, and it doesn't make as much progress as we would like. And another scalability problem that is rather problematic, and that I've seen a bunch of times in profiles, is that the buffer pins, which is this ref count field we saw earlier, uses SpinLocks. And if you have a page that is accessed very, very frequently, for example, the root page of an index, of a B-tree index, then that pinning process can be a problem again, because to increase this ref count, we don't use an atomic operation. What we do is we hold the spin lock, then do a bunch of checks, then increment it, and so on. And again, that only one process can do that at the same time. There actually are 2 patches sent to the mailing list like a week ago or 3 days ago that tried to fix this, and I think we hopefully can actually fix this for 9.06, but we'll see. How much time do I have left?
You have a lot.
Good, then I have more to say. I just thought that I can.
You have 15 minutes left.
Okay, cool. So this snapshot computation problem works this way. Every backend that's running has a so-called entry in the proc array, the array of running backends, and that says, my transaction with the ID so-and-so is currently running. Or in another case, hey, I'm currently idle, I'm not doing anything. Or in some cases, we can actually have more than one XID. If you have a transaction and then some save points, you have multiple XIDs. But what these XIDs are in detail is not actually that interesting. So, but the way currently the snapshot accuracy works is, again, we take a shared lock that is over this whole array. Then we go through it linearly. We say, hey, what's the status of backend 1? What's the status of backend 2? What's the status, and so on. And we then record that into a local data structure, which is then the snapshot. And that then contains, hey, the smallest XID we saw was this. The biggest XID we saw was this. And we have all these transactions as running. And if you imagine that you have a couple hundred or 1,000 entries of this takes a while. And the big problem, the prime problem, which has been alleviated a bit in 9.6, is that while this is going on, other people can also take snapshots. There's a big problem that all this memory has constantly been shipped to be shipped around between the CPUs in the system, which is a big problem, but still, it can happen concurrently. But the big problem is that you can't commit while this is happening, because this snapshot relies on being actually consistent. So you can't have somebody commit at the same time, which means that if you have many, many readers, they can actually prevent progress for writers. And until recently, every writer tried to get an exclusive lock over this array, then say, hey, my XID is now committed. It's actually a pretty small operation, but it needed an exclusive lock. And if you had 100 sessions waiting to be able to commit, they all had to wait and do it individually. What we now have is that we have a queue. These processes want to commit, and then the first one that actually is able to run says, OK, I'm committing all of these at once and do the work. Which helps if you have both readers and writers, or just writers, but it doesn't really help the complexity itself. It still is touches a lot of memory and is O number of connections open. So the alternative approach is here to replace all this here with a single number, which is kind of cool, but there's a lot of complexity to actually make that work. And I hope that somebody else works on this. Because I looked at the patch and, yeah, I had headaches. Yeah, So this is probably one of the biggest problems in Postgres right now from the scalability point of view. I hope that it gets fixed. So another problem is this. We have this extension lock, and if you just have like an unpatched Postgres binary, the way it scales, if you do like, it's a PG bench of many copies of relatively small files. The only reason I use small files of 1.7 megabytes is that it makes it easier to see progress with PG bench, because that only benchmarks how many commands were you issued. And the 200-something commands a second is not that much that it makes a noticeable, has a noticeable effect. And this was run on a physical hardware again, and that was thanks to Second Quadrant allowing me quick access to their hardware, which was pretty cool. And you can't really see this. It's with 84 gigabytes of shared memory configured, and on a machine that has 256 gigabytes of memory. And you can see that it's faster to use two connections than one. But it might still be faster to use 3, but after that it actually gets slower, which is really, really not what you want. And the problem there is, again, a copy into a single relation takes this extension lock, and we only ever take every insert basically, or every copy needs to extend the relation, so we constantly wait on this lock, which is why it gets slower pretty fast, because the only thing more processes achieve there is to say, hey, we have to switch around between more processes, but it's still only one backend that it can, or two that can make progress at the same time. So there's a couple experimental hacks to make this work. This is not a committed patch. This is not something we can directly apply, but it shows that if you do relatively small changes, you can make this scale a lot better. But you can still see that at some point you hit some scalability drop-off that's pretty bad. But I think it shows that we can do something about this and that it has the potential to improve things greatly. I wrote that patch, but I unfortunately think now that my approach was not actually that good. So I'm now trying a different approach. We'll see whether it works out, but it's relatively complex. If you are interested in such workloads, I would be very interested to see profiles from actual running like non-artificial workloads, because they tend to actually look different. This was just something I hacked up before a talk somewhere and the night before, so it's not the most representative thing here. So I'd be very interested to see. Sorry? It was last night? No. It was no. Last night I was stuck in an airplane without power for 7 hours. So no, this wasn't last night, but yeah. I would be very interested to see these profiles. In general, if you have a scalability problem that you think is like a CPU level, memory level scalability problem, please send profiles. Otherwise, we can't improve things, because what most of us developers do is they run pgbench or something easy to come up with, like running many copies that are of small files that all contain the same content. And that's not really representative of the real world, but we don't have constant access to the real world. So please send in profiles. It's not that hard anymore to do that. Install the perf tools package, or under Debian or Ubuntu-based installations, install the Linux-tools package and run perf record and then perf report. It's not that hard to do. There's a bunch of instructions out there, and send them to the mailing list. And then you'll say, people will say, oh, maybe you just need to upgrade to that version, or you say, oh, I've never seen that. Cool, we can fix that. So please, please, please do that. Or if you're actually interested in improving these things, just come to the list and try to discuss, hey, what can we do to improve this? There's many more people needed to work on these kind of issues. Yeah, that's what I have. Does anybody have questions?
You mentioned, if I heard right, that there could be scalability problems if shared buffers is too big.
Yes.
Is there some upper limit on shared buffers if you have a huge amount of memory that we ought to look
The problem is that it's a scalability problem to make it bigger until it's big enough. So
It's not going to be big enough then.
yeah, but the big enough there is not really whether it's that all your data needs to fit into memory. It's just that your hot data needs to fit into memory. If you read a page every, I don't know, 20, 100 times a second, a new page, that's not a problem. If you do it like 200,000 times a second, that's not going to work, but something in that range, that obviously that won't scale. So I would start try to increase it, whether it still works, and then in those cases it's better. If you hit problems, then you decrease it, and I think you will not see benefits lowering it below 4 gigabytes around-ish. That's my hand wave number. But it really depends very, very heavily on your workload. So it's unfortunately not like we can say it's exactly this number, because it really depends how many writes you have. That has a very, the more writes you have, the more likely it's to be beneficial to have large shared buffers. If you only have reads and everything fits into your OS cache, it's different. So it's unfortunately not a very easy answer to give. I think we should work on making this much easier to tune and much less this whole, hey, you make it bigger and it gets worse problem should go away, I hope. But we're not entirely there yet.
Having a certain amount of shared buffers be freed by a background process?
Yes. It didn't improve anything. The problem there is twofold. The approach might not have been good enough. And the other thing is that if you have one process doing that, it tends to grab all the memory to itself. So you have all the cache is now local to one CPU in a system. And you have like the other, or one socket, and the other 3 have no local data anymore. So you increase the bus traffic in the middle. Okay. I think it might help, and what I think might help more is to actually make the background writer actually write useful things. Because that currently doesn't happen, and that means that every backend has to write data to disk before it can use the buffers then. But I think the real approach is to have an algorithm that is not ON buffers.
Hey, listen, it was cutting edge for 2000? When was it we adopted the current algorithm?
Yeah, but it wasn't even then current edge. It was like we used it because the patent issues and stuff. Yeah. That was this whole mess.
But 2Q turned out to actually not be a very
2Q is pretty good.
But we did fix lock contention, but it didn't fix the thing that 2Q and ARC did fix. So we have one of those useful properties, that is to say, it's not a lock contention where you would, with a naive LRU, we'll say you would, but we still don't have sufficiently clever caching that weighs frequency as well as recency and adapts between the two. We need something that does that. That's my strong feeling.
I actually implemented like a pure LRU, and it was much better than what we have right now. Because the problem is that the current LRU is basically, hey, you have to search all buffers, and you don't necessarily need that for an LRU. And that also allows you to have like a much deeper, much more granular usage count, not like 5, which is far too low, because you can have n buffers basically, and that helped a lot. But it has concurrency problems of its own. Yeah, I think we are out of time.